Now we'll take a look at some simple triangulation algorithms that come pre-packaged with Grasshopper. They're kind of useful for generating patterns and also for partitioning point sets and spaces. They live up here in the mesh menu and then in the triangulation panel. So first of all, let's have a look at a couple of 2D algorithms that come with Grasshopper, starting off with the Delaunay edges component. Delaunay edges only has two inputs, some points to triangulate and a plane that is used to perform the calculation. So for the purposes of this tutorial, I'm just going to be using some of the components in the vector menu for quickly generating 2- and 3-dimensional sets of points. And so they're good for demonstration purposes, less good for designing because the points are typically random. So this point 2D component, for instance, will generate a 2D grid of random points, useful for showing you how this Delaunay triangulation component works. So you can see it outputs a list of points, which is the same data that the Delaunay component needs as an input. We'll plug it in, and it pretty quickly calculates this Delaunay triangulation. So the Delaunay triangulation produces these triangles between points such as the edges never overlap. It's also a minimal triangulation of these points, and so it's occasionally used in computer science and things for traversing graphs. But in our case, it's just a quick way of generating triangles which are always planar, so it's useful for fabrication. And if we have 2.5-dimensional sets of points, it can also be useful for quickly generating terrain. So I might really quickly give you an example of that. Let's say we have some contours. Going to reference them into Grasshopper. Again, it's just a demonstration. You'll learn how all of this works in later tutorials. I'm going to divide them up to get some points. We could use that for our Delaunay triangulation. And you can see it starts to create a terrain surface across those points. Now another algorithm which is kind of the sister algorithm to the Delaunay triangulation is the Voronoi algorithm. Instead of drawing edges across points, the Voronoi algorithm creates cells around points. So it has 4 inputs: the list of points to produce the diagram, optional cell radius for filleting the points, a containment box which will trim the diagram, and a base plane for the calculation. So if we use the same points, you'll see that now it's fitting cells around these points, and you'll also notice that the edges of the cells are perpendicular to the edges of this Delaunay triangulation. So these two components are used a lot in architecture and design for generating patterns, but the way these algorithms work, they're also quite interesting because we can make them generate recognizable grids as well, depending on the way these points are organized. So instead of using a random distribution of points, if we start using ordered distributions of points, like a hexagonal grid, the hexagonal grid of points will make us, let me just organize this quickly, equilateral triangles with the Delaunay component, and also hexagons with the Voronoi component. If we use a triangular grid and use the center points of those triangles, that makes triangles with the Voronoi component and hexagons with the Delaunay component, with these arbitrary triangles on the inside here. So you might want to have a look at what some of these other grids might do for these components. Let's quickly go back to our random. Another two-dimensional component we'll have a quick look at is the metaball. Now a metaball treats these points like electrical charges and fits a curve through a threshold where the charge is equal to a certain value. Now it has four inputs: the locations of these charges, the plane for sectioning the charges, a threshold for the value to fit a curve through, and the accuracy of the algorithm. So let's just plug in our points. You'll see that it makes this big blob around all of the points, but if we connect a slider to the threshold, we can control that threshold value and thus control the size of our blobs. Now let's take a look at some of the 3D triangulation algorithms. First of all, let's look at the 3D version of the Voronoi algorithm. So what it's asking for is some three-dimensional points and again an optional box to trim the algorithm. So I'm going to fill this box, which I've drawn in Rhino here, with points using the populate 3D component. I'll reference in this box using a geometry parameter. And this populate component will fill it with points. I'll make a slider to make a few less points, we don't need so many, and connect them up to the Voronoi. And you'll see that what it's doing is creating these three-dimensional cells within this box. Now this last video that you just watched, hopefully on state capture, we can do exactly the same thing here. We might bake it to Rhino, have a look at it in shaded viewport, and we could start deleting some of the cells, and you might start producing some geometry which you can recognize from some buildings or designs. Or even student projects. Very easy to do with Grasshopper. Another component that's I'll show you in the triangulation toolbar is the octree component. It's used a lot in the video game industry for reducing the amount of time it takes to search for things because it partitions space into a structured set of boxes. So what I'm going to do is I'm going to take this geometry here and I'll use again one of these grid components, populate geometry to cover it with some points, and then we'll see what the octree does to those points. So the octree has three inputs. It has the list of points to run the algorithm over, an option for creating square or rectangular leaves, and which are the names of these boxes, and the number of points to contain per leaf. So if we change the number of points per leaf, we're going to get smaller boxes. So it's just fitting boxes around these points so that every box contains 2 points, or 3 points, 4 points, etc. Now that's kind of interesting in Grasshopper because sometimes we can begin to approximate curvilinear geometry by distributing boxes across it, or it can be useful with box morphing, which we'll show you later on, for copying components across things. But it's also these two components, the Voronoi 3D and the octree, they can be used simply to generate patterns or as a form finding technique. So maybe you want to look at, now that you've had a look at these components, see whether there's any other components in the toolbar that you can continue using to build your own definition. So can you find components that take boxes as an input, or components that take polysurfaces or closed breps as an input, or maybe some curves, or polylines, or simple lines. You can also try playing around with the inputs to these components and different geometry in Rhino to see what you get, and make sure you bake things and keep track of all of the versions or iterations of your parametric model.